Assalamualaikum, hello and good day everyone. My name is Muhammad HAZEEM bin Muhammad HAKIMI and my metric number is MA250175. And in this video, I'm gonna talk about one of the most overlooked household item, and if not, a masterpiece of a palm-sized engineering, which is the nail clippers. While most people see this object as a simple grooming tool, in the eyes of a rigid body analyst, I see this as a high-pressure force multiplier. In this video, we are going to prove how this pocket-sized tool can multiply a light thumb press into a 120 Newton cutting force using compound leverage and static equilibrium. And this video also explores how the clipper works, how it balances itself, and why it eventually fails due to material fatigue. Without further ado, let's look into it. The chosen nail clipper here has an 80mm body length and also 75mm handle length and also 50mm height when standing upright. Based on its volume and material density, we have calculated the mass at 60 grams, where 20 grams is at the handle and 40 grams is at the body. But where is that mass concentrated? And using the composite centroid formula, we can use this formula to find out where it is. Using the composite centroid formula, it is found that the center of gravity for this nail clipper to be approximately 62.5mm from the pivot. This is considered as the balance point. To prove it further, if I try to support the clipper here using one finger, it stays in equilibrium because the moment created by the mass of the body and the handle cancels out. Now let's take a look at the first stage of the machine, or the free body diagram of the handle. This is a class 2 lever, and the pivot pin here acts as our fulcrum, and when I apply a 15 Newton force at the tip, about 70mm from the pin, it can create a clockwise movement. To maintain rotational equilibrium where the sum of moment equals to 0, the jaw pushes back against this small wedge just 7mm from the pin. Because that distance is 10 times shorter than my thumb's distance, the force is multiplied by 10. We are now sending about 150 newtons of force down into the main body of this nail clipper. Now here we have the free body diagram of the lower body, or the lower part of the nail clipper, and this is where it gets interesting. The jaws here act as a class 3 lever, and the fulcrum is all the way at the back well, and the 150 newtons force from the handle previously we calculated hits the jaw about 64mm from that back well. And even though a class 3 lever technically reduces force, it is necessary for the range of motion. By the time the force reaches the blade at 80mm mark, our equilibrium equation tells us that we have 120 newtons of output. That is an 8-to-1 total mechanical advantage. We have effectively turned a 1.5 kg push into a 12 kg crunch at the nail. The handle of the nail clipper functions as a class 2 lever, which previously mentioned. In this configuration, the fulcrum is at the one end, and the effort, which is the thumb pressed at the handle, is at the other end, and the load, or the resistance of the jaws, is located between them. And for a rigid body to be in equilibrium, two conditions must be met. First, translational equilibrium, where all vertical forces must cancel out, and also the rotational equilibrium, where the sum of moments about the pivot point must be 0. And referring to the free body diagram of the handle, we can apply an average input force. In here we choose 15 Newton to put at the end of the handle, and using the formula of rotational equilibrium here, we can find the force that exerted onto the jaws, also called as the F jaw, to sum the moments around the pivot P. And by using this formula, we can put the values and rearrange the formula to solve the F jaw, and then we will get the F jaw to be 150 Newton. Now that we have determined the force applied by the handle, which is 150 Newton, we must analyze the lower assembly or the jaws of the nail clipper as a secondary rigid body, and this stage determines the final force delivered to the nail. And while the handle was a class 2 lever, the jaws function as a class 3 lever, and in this setup, the fulcrum is placed at the very back where the two metal plates are welded or pinned together, and the effort is applied in the middle by the handle, and the load or the nail is at the far end. And while class 3 levers actually reduces force, they allow for a wide opening and precise control of the cutting edge. And using the same formula we used previously, to find the final cutting force or the force applied to nail, we have to sum the moments about the rear joint, which is the sum of the moment at the back is equals to 0. And applying the formula, we can summarize that the force applied onto the nail is approximately 120 newtons. After discussing the magic and inner workings of this incredible tool, why doesn't the clipper stay closed when we exert a very large force onto it? And the answer lies in the Hooke's law. Here, the steel here subconsciously acts as a cantilever spring, and as long as we stay in the elastic region, the metal lattice can always return to its original shape, regardless of how many amount of force exerted onto it. However, rigid body equilibrium assumes that the parts stay aligned. If the pivot pin wears down, we get misalignment, and this creates a lateral torque that shifts the blade, and instead of high pressure shear, you get a slide in which old nail clippers stop cutting and start tearing, which can damage your nails in the process. In conclusion, the nail clipper is a perfect study of statics. It used two lever classes and principles of a rigid body equilibrium to solve a biological problem with mechanical precision and accuracy. This project was researched, calculated, and produced entirely as a solo effort. This object here is truly an engineering marvel. Thanks for watching the physics of everyday. Assalamualaikum.